Good afternoon from Hellenic Mediterranean University and Athena European University. It's a great pleasure and honor to have today with us Irka Hajdas from ETH Zurich. She's also affiliated with the Polish Ecotech Complex Center, as far as I got to know just a few minutes ago. It's a really interesting topic that she will present to us today. It's a timely topic, I would say. The title of the presentation is Old and Young Carbon, the clock made in the universe. And few things about our today's speaker. So she is a senior researcher at the Laboratory of Ion Beam Physics at ETH Zurich in Switzerland. She studied physics at Jagiellonian University in Krakow, Poland, and gained her doctorate degree from ETH Zurich, where she is located today as well. And she is involved in teaching at the Department of Physics and is a lecturer at the Geology Department at the ETH Zurich. So again, it's a great pleasure and honor, and we are really interested to hear your talk. So please share your screen and start your presentation. You have 45 minutes for your presentation and around, let's say, 10 minutes for the Q&A session. Thank you very much.
Okay, thank you very much for the introduction. I will share the screen. I hope it works now. All right, it's there. And I will right away, I want to start. Oh, no, I cannot start my pointer, but I will move with the mouse. Okay, thank you for the introduction, George, and thank you for having me for this series, which I started to follow recently, and I see there is a lot of exciting and very modern development. I might say that it's a little bit, I don't know, my title says it's a bit, doesn't sound esoteric maybe, but it's not really. As you said, I am a physicist, and this radiocarbon clock that I am going to talk about it's basic physics, starting from the production of the radiocarbon, and then we might think about this going deep into different aspects of our lives. So yeah, again, all my affiliations here, and I'm really happy to be able to join on a from the site of University of Marii Skłodowska-Curie in Lublin. That is how I found out about the series. Moving to the talk. I hope it moves. Yes, I will have, this is my outline. I will talk a little bit about radiocarbon because maybe some people, I know it's a lot of information in media also. So some people know about this, and I'm sure many people have seen this Iceman, Ötzi, as they call him, found on the border between Italy and Austria. And how we found out that this mummified body was really quite old, and that was the exciting news 30 years ago. So it's a very perfect example to show the half-life of radiocarbon. As I said, a little bit of physics. Radiocarbon is a radioactive isotope, which has the half-life of 5,700, almost that is the time when Ötzi lived. And I will talk, I will give you just a few examples of the applications, how we do it today, starting with our samples, let's say straw from Ötzi's cloth, and then how we proceed. Here, this again is physics. That's why I am in ion beam physics at ETH. We measure, we count atoms of radiocarbon, and based on this, we build the chronology. Or we can talk about C14 as a tracer. So now to my, not esoteric, but to my title, how I created it some time ago when I was talking to antiquities dealers or specialists. Long time ago it was, and they were, of course, interested in old objects, but this old and young words, it's a play that we see in our method. Old carbon is in us. I think Joni Mitchell had a song a long time ago that was saying we are billions years old carbon. We have stardust in us. Most of carbon in us, in our surrounding, is an old stable carbon produced in supernova explosions in formation of the universe. And then we have the young carbon, which is the radiocarbon, which appears in our surrounding on this very, very low level. This is 10 to minus 12 if we measure the ratio between C14 and C12. And this young carbon is again created thanks to the activities of the universe. That is the very energetic cosmic rays. You can see here the picture of a cascade, cosmic rays hitting the atmosphere and producing cascades of particles. And somewhere on the bottom of this cascade is a thermal neutron, which is the agent that is important for us. In this cartoon, you can see the production of C14, that is neutrons. They are secondary particles produced from these cascades. Neutrons meeting nitrogen, we have C14 and protons. And again, this very, very low concentration, 10 to minus 12. This is important in the whole application procedure, how we will talk about this. And then you can see C14 is carbon. So it joins the carbon cycle. It's oxidized to CO2 and joins and fixed into organic matter through the photosynthetic path. Oh, sorry. And maybe still important to point out this exchange with the ocean. The ocean is a huge carbon reservoir, almost 70 times larger amount of carbon than in the atmosphere. It's important for the complications of radiocarbon that I will not really talk about it. How the clock works, I already mentioned the photosynthetic path. Here we have this C14 fixed from the atmosphere almost simultaneously. So we have the C14 in the green leaf foliage on the reflecting, showing the C14 concentration of the atmosphere. And then as long as the leaves are living, or the sheep is eating the grass, it remains in the equilibrium with the atmosphere. As soon as this path is broken, no more exchange with the atmosphere, we have the clock starting to tick. And as already mentioned, the half-life, that means halving of the concentration, happens for C14 after 5,700 years. These are examples. Here is a wool that was found in Scythians Kurhans. This is some other type of textiles, actually made of bast from trees, and you can see here quite old settlements in Turkey. So that's how it works, and this is what we measure. We measure the concentration of C14 in our sample. That is measured at the time t, and A0 is our assumption. This is important now. It's our assumption of the concentration concentration in the atmosphere here in this green area. And of course, we have the lambda for the decay constant and connected to the half-life of C14. This was established in, let's say, 1949 by Libby and his team, his students. He established this method and started to measure all kinds of materials for the measurement of time with the equation which I just presented. What he did, he was, because as we said, radiocarbon is radioactive, so we have here this beta decay that allows us to detect or measure the activity of radiocarbon. Back then, it has been done by counting the particles, and here is Libby with his detector that he used for measurement of different types of materials. Nowadays, I already pointed this out, we measure, we count atoms that are C14 atoms that are still present in our sample, and we establish the fraction of remaining radiocarbon. This is a figure that is showing the whole path, starting from sample through the measurement, and then our values, this fraction 14C, this is AT over A0, that we, of course, with various corrections and calibrations, we measure this and use for our calculations of age. Here is just a few insights into samples, how they look like, how the process looks like, what we at the end, you can, maybe it's important to point out, we are able to measure this little amounts of carbon down to 1 milligram or even down to 10-50 microgram of carbon. And below is the figure showing the machine, how it looks like. And just comparison, if we start with something like this here in the sample before the whole processing, in the end, the sample fits into this target that is then finally placed in an accelerator for the counting of atoms. This is just to mention the complications. The method is simple, but it has complications given to or predefined, given to us by nature. It's not as wonderfully as simple as assumed by Libby back when he established the method. The A0 that we need for calculation of radiocarbon age is not constant. Nature is much more complicated. We need to calibrate our radiocarbon ages. And I just show this cartoon again to point out the complications. Where do they come from? Here it comes, and we all had this in news. We had polar lights in Poland. Unfortunately, I didn't see that, but the production rate of radiocarbon is connected to the shielding around the Earth, the shielding given to us, or predefined by geomagnetic field, but also by solar activity. The stronger solar activity, the lower the production of radiocarbon. There is less cosmic rays coming through to produce C14. And then I mentioned the ocean, which is a huge carbon reservoir and has an effect on our C14 signal around the ocean, but also globally. And last but not least, it's us changing the C14 signal through the, first of all, starting with Industrial Revolution, First of all, Suess effect is combustion of fossil fuels, and then later, after the Second World War, we had the thermonuclear tests that created so-called bomb peak. I will show this later. So we have, people found ways to correct for this, and we go back or we get help from our sister geochronological method. Dendrochronology, for example, gives us a wonderful opportunity to correct by combining the dendrochronological work going back. Now we can say back to 13,000 chronologies put together like this. This is an example from the States. And then through radiocarbon measurements on well-dated tree rings, we are able to have an experimental calibration curve. And here I have only the last 2,000 years of the calibration curve, just to show you the complications that arrive from this not constant A0 of the atmosphere. And you can see that ideally, for everyone, ideally would be the line should be just line as assumed by Libby. But unfortunately, for many users, I'm not saying for everyone, because for radiocarbon researchers, this is what keeps us excited and busy all the time. We have more than, we don't have the straight line. We have those so-called wiggles that sometimes create problematic chronologies, or not so very simple. Nevertheless, we have a very wide range of applications, and here I just I list this what is most common, most the oldest, let's say, with anthropology, archaeology, and paleoclimate research. Radiocarbon method took off in the 50s and 60s of last century. This was the eye-opening application. That is maybe a good moment to start with the natural archives. Just an example from a lake that has been formed after the glaciation. This is the lake in Switzerland. As I said, I'm based in Switzerland, so I have a few examples from Switzerland. But of course, there at the time when, and I worked on this lake as a PhD student at the time, similar, even if not better lake was studied in Poland, also Lake Gościanz. We were kind of competing at the time. So this lake, on one hand, provides a chronology of the last of the climatic change in the last 16,000 years, but going and I jump to this side also here to mention that we might go to any site around the world and look at the records. And then with the help of radiocarbon, we will have the chronology of each of those records most of the time. Sometimes it's complicated, but most of the time it works very nice. And for Zoppense, it works so nice that later a PhD student started her project on looking at the changes around the lake. Not only looking at the chronology of the sediment, which is here in the bottom, the deposition of layers through the years tells us what happened around the wreck. Later, Merle looked at the biomarkers in those sediments to read the past of the catchment area. That means actually the changes in a catchment that were introduced by the climatic change, but maybe also humans. She separated biomarkers. This is chromatographic separation of alkanols and fatty acids. And she could see that this well-dated record that we have to here sediment depth, and here we have radiocarbon age. We have the chronology based on small fragments of organic matter, macrofossils we call them, and it shows a nice agreement between those alkanols, which are we know that they were in a soil that was coming into the lake. It is quite stable until 4,000 years ago, as archaeologists working in the region know, people came and, and they disturbed the region so that very old organic matter went into the lake, was washed in. So this is one of the newest, let's say, the last 10 years application of those methods dating biomarkers in sedimentary record is quite successful and wide used in not only in lakes but also river sites and ocean and soils. I jump to the very last part of the radiocarbon timescale, as we say. The radiocarbon method works back to 50,000 years. This is limitation given by the half-life. And again, in Switzerland, we have this wonderful example of the almost the last material that it can be dated using this method. The mammoth site that was discovered more than 100 years ago on the limit. Here is Zurich, and this is the limit of the last glacial extent. So it was just luckily sitting outside of the glacier, and the glacier didn't destroy it. People found it in first constructions of the railway, and then again more than 20 years ago. You can see here that this mammoth is maybe put together not properly. This is a postcard from the very first how they put the bones together. The site had quite a few mammoth bones, and I think the bones are still there. People, if they built houses, they still found bones. The question was, of course, how old is this this site? You can see here, this is the mammoth, almost 50% of it, this 2004 years excavations. Bones of mammoth and other animals and the pit section. We dated it to find out when it was, and this is a question how we correlate records like this, climatic records of sedimentary deposits on the land with, say, we have here Greenland reconstructions from ice core drills that we have, we know how the climate will Delta-18. We have this cold warm events with Holocene on the top, very warm. And now the question is, where is the mammoth? And as I said, it's almost the end of the radiocarbon calibration curve. We measure 45,000 C14 years. With the calibration, it's almost 50,000. And you can see here, we place it at 50,000 on this warm period. So how am I with time? 12:30. Okay, so I think I can still talk a little bit about the applications, classic application, and archaeology, I mentioned at the beginning, archaeology is a big driver of the radiocarbon driver user, a big supporter also in developments. And I've been working with archaeologists from Switzerland, but also archaeologists working outside of Switzerland. And this is the example from work that the University of Geneva is doing in Senegal. This project is going on for more than 10 years now. I've been involved for 10 years, and this is probably a nice way to memorize the last 10 years of measurement of radiocarbon ages. Each year they would go to the field and to bring among with other archaeological objects. They would always look for charcoal and material that it can be dated. And quite recently, a publication came out that summarizes this work. And you can see here, it's not only about the recent archaeology, but also looking at geomorphology of this region. That is the river erosion and changes, climatic changes. You can see that going back to 20, even more, I think that below is even more of the record. We can go with radiocarbon down to 20,000, but it's not so easy to find the material back there that it is datable. So the other method applied here, OSL, optically stimulated luminescence, is the I say sister method here that provides this information. You can see here that this one points to the deepest potsherd, that it's dated to 6,000 years, and the oldest charcoal samples so far measured there. Maybe we cannot say from charcoal, is it human created charcoal, or is it natural fires? Nevertheless, 15,000 years. Going back to younger parts of archaeological applications, I wanted to point out another way of dating using radiocarbon, and this is the same, measuring the C14 in remaining in samples. However, the samples are not organic. That's not charcoal, that's not wood, but it's the C14 that is bound to CO2 when mortars, the parts applied for construction sites, are binding. And this method has been developed by mostly Scandinavian laboratories. It has to some extent applications down to Roman times. I have this example again from Zurich, and this is my favorite church in Zurich, but maybe also known by some of people who visit Zurich, because it has windows, glass windows by Marc Chagall from Münster. This church was built in 850 Anno Domini, and you can see here that we, together with archaeologists, we try to date this C14 bound to mortar. We try to date this, and the first attempts, which are still not published, but kind of promising, because we are definitely not of the we meeting this time that is provided by the documentation. So that would be transition to our modern times. I already mentioned our anthropogenic effect on the C14 in the atmosphere. And here, I want to introduce the C14 bomb because this is one of the this is a tracer that we in radiocarbon dating apply into various studies. So the bomb peak, as we know, after the Second World War, the nuclear tests started to take quite high speed, and development of thermonuclear bombs was tested. The first test can be detected in radiocarbon. You can see here. Here we save a fraction 14. That means we're measuring C14 in the atmosphere. This is before the World War. Before the World War, natural level 1, a fraction 14C at level 1. It's the natural that we would expect over the times. So this development was detected by people doing radiocarbon quite soon, and the following measurements allowed to, and the measurements that continue to go on allowed to reconstruct this variability that you can see here. We have northern hemisphere and southern hemisphere at a little bit different levels. Nevertheless, the change in C14 that we observed, it's somehow closed. I cannot see my figure here. I should. It's, if we arrive to 2020, you will see that we are at the level of a fraction more than equal 1, and actually now measuring the current atmosphere, we are going into older atmospheric, into older radiocarbon ages. This is, I would say, quite a pity, because we have a whole suite of applications that uses this radiocarbon bomb peak, or use this radiocarbon bomb peak. And you can see here the publications that present such studies, I'm sorry, can be found in this paper. You can see here that biomedical applications used quite a lot of radiocarbon signal. Each part of our body behaves differently in terms of exchange of carbon. And by studying of tissue, for example, fat tissue, people can say how the fat is deposited, or it can help people to sorry, to find ways of medical treatment, or understanding how the other parts of body are exchanging carbon. It's helpful in prevention or also treatment. Also, it is a tool that is helpful in forensic applications. So, for example, looking at identification of bodies. And I have the example from our lab. This is, if we think about teeth, this is an example from a student who came to work on during the week school project. She or him brought their milk teeth, and we analyzed that. That was 2016, and you can see here, actually, I can't see because I have to move this, that the students were around 17, 16, and you can see here, this is the time when they were born. So that measurement really indicated the time of birth. It has wider applications. We have here a paper that is from Italian group. They present method also used quite frequently to detect the illegal poaching of ivory for the protection of elephants. So this is not only one of the methods that we can apply radiocarbon to. Right, I think I still have 5 minutes, right? So I can present the application of BOMPIC for the detection of forgeries in art. We use the same approach. The signal of the BOMPIC will tell us that something is from the last, from the time period between 1950 and nowadays, we say 2020. And here is the cartoon, let's say, showing combination of the paint here and the canvas. The canvas is easily there can be old canvas applied to paintings by forgers because it's easy to get an antique painting and create something that may be more valuable or appears more valuable. However, the paint contains oil. The binder is an oil. It's not natural product. And this binder here might be our way to detect forgeries. And you can see here, and this is a real case that we detected. It was the binder that told us that the painting was a forgery from 1980. You can see here, the C14 signal is from 1980, but the canvas was dating to the beginning of 20th century. Similar to objects that are made of wood, we can detect the last 70 years thanks to the BOMPIC. And I have this real example of a Malevich painting, which is now in Düsseldorf, and it was for a long time really shown as a Malevich painting, but then at some point investigations, art historians, researchers looked at the painting closer. You can see here in blue, I pointed out what is interesting, this pencil underdrawing showing someone really working on a forgery. And then finally, the colleagues sent the sample to us, and you can see here, this is dating to 1975. As we know, Malevich would be beginning of 20th century, so it's clearly a forgery. However, this wonderful tool of the BOMPIC, it's gone. We can say now it's gone because of this overlapping anthropogenic effect that we have here. It started even before the BOMPIC, the Suess effect, combustion of fossil fuels. Here, the methane being burned somewhere in Siberia. We have emissions of old CO2 that it dilutes the atmosphere and it makes the atmosphere older, so old that nowadays we are here, right? This is the bomb peak in different units, but however, this is the same fraction, 14C. We are here, we crossed the line of fraction 14C1 or 0 in these fluctuations units. And you can see, dependent on what we will do, and I'm afraid we are somewhere on this path here, the atmosphere in 2100 will be as old as 2000 C14 years. So that means we will be collecting living leaves and measuring radiocarbon ages on the level of 2000 years, which is quite a shocking future. And we would all hope for the green path of the really reduced fossil carbon emissions, but we don't know. So this is what my students measure at Hengeberg here, where we are based. We collect leaves, so you can see here, 2020, we crossed the path, and we are really down here below the natural level. And I think this is all. I still think radiocarbon is the most useful tool for multiple research fields. Over the 70 years, the technical and methodological developments were really amazing and allowed to expand the field to various applications, such as this biomedical, what I showed you. The fossil fuel combustion is making our life difficult, not only climate-wise, but also C14-wise. And I really hope that other disciplines will be using the radiocarbon more and more, and maybe spreading the word. Thank you.
Thank you very much, Irka, for the very nice presentation, very detailed one, and congratulations for keeping, the timing very sharply. Now it's the time for the Q&A session. So if someone has a question, you can raise your virtual hand or type your question in the chat. Let me see the chat. I don't see. Maybe I can start with my... please mute your microphones. Maybe I can start with mine. It's just out of curiosity. Of course, I'm not expert in the field. So I would like to know a bit more the details about... I saw in your presentation you are using graphite for your methods somehow. So I would like to know what is the actual contribution of graphite in your predictions, and how the graphite quality, for example, if it is natural or synthetic, affects your prediction models. This is my first one.
Okay, so this is actually, I cannot go back simply. I will, if yeah, it somehow doesn't, should jump. Okay, so the graphite that we're using, it's actually graphite that we produce from our samples. So that is the CO2 that is from the sample. Would it be a leaf, or would this be a bone, or at the end we combust the sample, or if it's a shell, we would dissolve it in acid, and the CO2 is then graphite. We call it graphitized, so reduced to graphite. We use hydrogen and iron as a catalyst. We have a bit of iron as a catalyst, and the hydrogen and warming of the mixed CO2 with hydrogen, we graphitize this. I think it's an old method that people developed for other reasons, I think, for collecting of CO2, also removing CO2.
Okay. Thank you very much. Could you please stop sharing your screen so that we can have a more let's say, interactive conversation. Thank you very much. I see, George, you unmuted your microphone. You would like to ask?
Thanks a lot for your presentation. I wanted to ask you, apart from the knowledge that is necessary to do these things, what about the infrastructure? I mean, does this require a lot of, devices and things, or is it easy to do it?
Okay, thank you for the question. Actually, it was a hard choice what to put on the side. There is, as you see, we use AMS, accelerator mass spectrometry, which is nowadays, as many facilities were formed around the world. And as if I can think about it, I think it goes to 150 facilities around the world. I don't know of any in Greece. I think there were attempts. We would like to have also one in Egypt for the archaeological reasons, but I don't think there is a facility in Greece. That is definitely, and there is a slide that shows the distribution of that and how the machines are costly, maybe up to 2 million euros. But there is the whole new generation of facilities that are smaller and smaller. So I would actually recommend, if our address is simple, ETH Zurich, and you can find our webpage ams.eth Zurich. We have all kinds of pictures and links that show this. Those facilities, because the group that I am in, they were involved in creating new generation of machines that are now commercially built by a company or companies actually. Yeah. So yeah, it is not cheap. It requires investment of a couple millions probably. Okay. But it makes sense if there is like a departmental use of it. And I was trying to show this, that there is such a bright palette that you can do with radiocarbon. It's not only archaeology, it's not only climate change, it can be environmental, and it can be forensic, it can be, yeah. So that is I was hoping my message. Yeah.
Okay, thanks a lot.
Okay.
Thank you very much, George, for the question, and Irka for the answer. There is a question in the chat, so I will read it for you. From Ninke Moens, if I'm pronouncing the name correctly. The question is the following: I'm also not an expert in the field, but I would like to know how you stimulate interdisciplinary project for your students. Does it flow naturally from the project, or do you need to involve your colleagues actively from other faculties?
Okay, thank you for the very nice question, because yeah, it is actually I took care of the lab, so to speak, user lab. That is how I built up my research. So it was me, when people were coming with samples, that I was interested in their research, and I followed on up. Nowadays, quite a lot of archaeology departments, they have new curriculum. People come, students come with clear projects. But yeah, it needs both. I think it needs interest from your user, and it needs also your interest in, well, at least from the radiocarbon researcher side. There must be this, curiosity for application. Yeah, thanks.
Thank you very much, Nimke, for the question, and Irka from the art for the answer. Is there another question for our speaker? Maybe I would like to ask you about, you mentioned also the anthropogenic contribution, like the nuclear tests, etc. What about the nuclear accidents that happened a few years ago, I mean, in Japan or here in Europe? What about this contribution?
I know people use this for other isotopes. Our group is actually doing all kinds of isotopes. So we do also uranium, thorium, and iodine. For radiocarbon, the facilities that are producing radiocarbon, like not even accidents, maybe there is a release of some gases, but it would be locally. It is not on the extent that we see for the bomb peak as it is. It was produced through the tests that were stratospheric. So that's why it went globally. And even if you think of this curve that I showed, Northern Hemisphere is higher and it's earlier because the tests were in the Northern Hemisphere, and the produced signal had to be mixed within atmosphere. It took like a year. And actually people used that signal to study how the atmosphere was mixing. That was back then in 50s, 60s, yeah. But now local signals, they can be detected, but not on a global level, maybe not on a very regional level.
Okay,
but
clear.
Definitely there is a monitoring. I know in Switzerland we used to do this as a user lab. We used to analyze samples for monitoring leaves around the power plant to see if there is. It's not a very quick method, but you can detect them. In a tree ring, you can detect such events if that happened, actually. Yeah.
Very clear. Thank you very much. I can see still people joining the call. A bit late, but it's okay. So any other question or comment? If this is not the case, let's thank once again our speaker from ETH Zurich, Irka Hajdas. Thank you very much for your excellent contribution, and we hope to see you in another Athena talk in the coming weeks. Thank you very much, and enjoy your
Thanks
weekend.
a lot.
Bye-bye.
Bye.
Bye.
Have a nice weekend.
Goodbye.
Bye.